Welcome back, everybody. We are looking at example 1 on page 110 of the workbook. And let's read this together. They're giving us a vector field f, 2xi plus 2yj. Okay, and they're asking us to use the fundamental theorem of line integrals to calculate line integrals along a series of paths. Okay, and notice that in parts A, B, and C here, they're describing three curves to us, C1, C2, and C3. We can see those three curves over here in our picture. So we've got a line, a parabola, and then another line. Okay, and before we dive into this, one comment I'd like to make is that we could do this problem using techniques from sections 18.1 and 18.2. We know how to parameterize curves. Okay, so you could do all three of these integrals the old way. Okay, but you know that parameterizing curves, that's kind of a long process. So that would be quite a bit of work to do all three of these integrals using the old way. Okay, this question is asking us to use the fundamental theorem of line integrals, which will hopefully provide us with a shorter way of obtaining our answers here. Okay, well, the key to using the fundamental theorem of line integrals is we need a potential function for our vector field. Okay, remember what a potential function is. It's just a function whose gradient agrees with our vector field. In other words, we want a scalar function so that the derivative with respect to x of it equals 2x, and the derivative with respect to y of it equals 2y. That would make our vector field equal to the gradient of this function little f that we're looking for. Okay, so we're going to start with that observation. We know that if there's a potential function, little f, its derivative with respect to x has to equal 2x, and its derivative with respect to y has to equal 2y. Okay, and the question is, if those are the partial derivatives of the function little f, what is the function? Okay, well, we need a function whose derivative with respect to x is 2x. That means we're going to need an x squared, because if we take the derivative of x squared, we get 2x. And to get a partial derivative with respect to y of 2y, we need a y squared. Take the derivative of y squared, you're going to get the 2y. Okay, so it seems reasonable that x squared plus y squared might be a potential function. Let's do a quick check just to be sure. Okay, when we take the gradient of this f that we've written down, does it really give us our vector field? Okay, well, take the derivative of x squared plus y squared with respect to x, you're going to get 2x, and with respect to y, 2y. And notice that that is indeed the vector field that we started with. Okay, so we have a potential function sitting right there. All right, and once you have a potential function, it actually makes calculating line integrals pretty easy. Okay, let's start with part A here. So they would like us to calculate the line integral of our vector field along the curve C1. Okay, and so we don't have to do any parameterization here. The fundamental theorem of line integrals says that this is going to be equal to our potential function evaluated at the starting and the end point subtracted from each other. So 0, 4, and 3, 1 are like the p and the q in the fundamental theorem from the previous page. So all we need to do this calculation is to take f of q minus f of p. Okay, and we have a formula for f sitting right up here, so we're just going to substitute those numbers in. So f of 3, 1, we're going to take 3 for x and 1 for y. That's going to give us 3 squared plus 1 squared. And then we're going to plug in 0 and 4. That's going to give us 0 squared plus 4 squared. And you can double check my arithmetic and confirm that that gives us -6 for the value of the integral. Okay, we were able to do that integral without doing any parameterization at all. Okay, let's move on then to part B here. Okay, same type of question. We're being asked to calculate a line integral, but this time along a different path, C2, which in our picture is this parabola that we're looking at here. Okay, but again, because we're using the fundamental theorem of line integrals, it really doesn't matter what the path is that we're traveling along, only the starting and the ending points matter. Okay, 0, 4, and 3, 1. Notice that those are exactly the same points as in part A. And so we're going to get exactly the same answer that we did in part A. Okay, our potential function up here, f, little f, has not changed. So this is exactly the same series of substitutions that we did above. We're going to get the same answer. Okay, so this illustrates why it is that we call a conservative vector field a path-independent field. Okay, it totally didn't matter what path we went along. We had two curves, C1 and C2, in parts A and B, and they happen to share the same starting and the same ending point. And we have to get the same value for the line integral if that's the case. Okay, now at this point, I'd like you to maybe pause the video and see if you can do part C on your own. Okay, so I'm going to pause for a minute and let you do that. Welcome back. Okay, so let's confirm and see if we got the same, see if I get the same answer as you did for part C here. Okay, same thing that we did above. The only thing that's changed is that we've got a different starting and ending point. So this time we're going to take f of 4, negative 1 minus f of 1, negative 1. And then it's a matter of going back to our potential function and just substituting the pieces in. So x squared plus y squared is 4 squared plus negative 1 squared minus 1 squared plus negative 1 squared. Okay, and if you do the arithmetic there, you're going to come up with an answer of 15 for that third line integral. Okay, notice there wasn't a lot of calculation that we had to do. Okay, we didn't have to do any parameterization, really. The only real work that was involved here was finding this potential function. Once we had that,